Hey guys, it's Gus from Leetcode Solutions, and today I'll be looking at the fourth problem, median of two sorted arrays. And this one is a bit of a doozy. You can see it's labeled as hard by the website. The hard part of finding the median of two sorted arrays isn't actually finding the median, it's making sure that you do it in O of log of n plus n time. So I'll just quickly read the problem statement. Given two sorted arrays nums1 and nums2 of size m and n, respectively return the median of the two sorted arrays. And remember, again, we want the overall runtime complexity to be O of log of n plus n time. I've done this problem before, so I know the intuition, but I can tell you right now that it's not easy to immediately come up with the plan of attack. It's something you want to look at this problem and really try and digest all of the information it's giving you in the problem statement first. So the first thing that jumps to mind for me is that since we're looking at it, we're looking at trying to solve this in O of log of the input size time, then we should at least consider that we're going to be doing some sort of a search on our inputs. Note that our inputs are sorted, and if you do a search on a sorted list, it will take log of n time, or log of n plus n in this case. And I'll show you why. Let me just open a Word document here. Say we have a binary search tree, and I'll just draw two levels. That is not a very pretty looking tree, but hopefully you guys see that that is in fact a binary search tree. If we were looking for an element in this tree, we know that it would take, at worst case, 1, 2, and 3 steps. Worst case being that the element is at the bottom row of the tree. That because we take one step here to look at this element, another step after deciding which element to look at here, and another step to deciding to look at which element out of these four, depending on if we've gone this way or this way. And note that our input size for this problem here is 7, because we have 1, 2, 3, 4, 5, 6, 7. But maybe a better way of looking at that is that it's equal to 2 cubed minus 1. For a very large tree with k rows, it'll be 2 to the k minus 1. Point being that the complexity in this situation is 3, right? It takes 3 steps at worst case scenario to solve this problem, and log base 2, that's what we use in computer science, of 2 cubed minus 1 is approximately equal to 3. And that gets closer to being true once you do a large K. It's going to be approximately equal to K, which means that this value here is equal to our input size n. So you could say that our complexity is equal to, worst case, O of log n. Okay. The other big hint from this is that we're looking for the median, and you want to consider what the definition of a median is. In math and stats, the median is the element that separates two groups of numbers by their magnitudes. One group with magnitudes smaller than the median, one group with magnitudes larger than the median. So with that in mind, you have most of the tools necessary to be able to solve this problem. You want to try and find the specific element that separates those two groups. And you want to try and do that with some kind of a search. Binary search is what we're going to try here. And let's get a new page going to try and maybe show you the plan of attack here and why it'll take as long as it does. So let's draw a very basic example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hope you guys had this part on 2 times speed. So what we're going to want to try and do here is we know that the element is going to be in one of these 2 arrays. So we're going to want to do some kind of a parallel binary search. We're going to be searching both of these arrays at the same time for the element and find if the elements we're looking for, if one of the 2 elements we're looking at meets the requirements. And if not, we will look at different elements. And what are those requirements? Well, take a look at this. Say 4 is less than 13 and 12 is greater than 5. But say this were some number that were less than 5, and say all of these numbers were also less than 5. Then we would have 2 elements that this number here is lower than all of the numbers on this side, and this number here is lower than all of the numbers on this side, but they are also greater than all of the numbers on this side because these are sorted arrays. So what we would want to do then, we would have the information ready to find the actual median here because we have found the 2 groups that are separated by the median. So what we would do here in this specific instance, because this is an even amount of numbers, is we would want to take the maximum of these 2 numbers and the minimum of these 2 numbers, because the max of these is the greatest element in the low array, and the minimum of these would be the lowest element in the larger array, and find their average, and that would be the median of the entire array. If it were odd, we would just find the maximum of the 2 lower numbers. We don't need to do any averaging. The element would be the separating element. But let's go through and actually find the real median for this list. So we know that 4 is less than 13, but 12 is greater than 5. But 12 is right now, if we look at these as partitions, it is not on the side that of the lower elements. So if we're doing a binary search, what we probably want to do then is cut it to this point, make this our new partition over here. In fact, you know what? Let's just make this a different color. And then make this our partition over here. We know our median will then be on this side somewhere and on this side of 12 somewhere, right? Over here we have a similar situation where 10 is greater than 7, 6 is less than 11, but that doesn't matter. Make a new partition, half of the size of this, what's left over, half of the size of this, what's left over. 7 is less than 10, but 9 is greater than 8. And we're on the very edge, so then we can choose, okay, well, looks like 8 and 9 are our only elements left over here. So we would simply get 8.5, which is the average of 8 and 9. Okay? And so with that in mind, let's try and take an approach. I guess one other thing we should probably mention is that to find the starting spot in the starting spot for the partition in one of these arrays, in the lower array, we want it to just be half the size of the array, right? In the smaller array, I should say. So let's say the smaller size is equal to size m. So the first partition spot we'll call P1 is equal to m over 2. But, you know, they're not both of these are not going to be the same size. What we want to do is choose another partition spot that has that allows for an even number of elements to be on the left side and the right side in total. So what would that mean then? That would mean P1 plus P2 is equal to m plus n over 2. And could be an odd number, so let's just do n plus 1 over 2 and the integer value of that. I know from experience that if you just leave it as n plus n, it doesn't work. You want to make sure that it's n plus 1 over 2. And from here, what would that mean that MP2 is? The second partition, you would start it out as m plus n plus 1 over 2 minus P2 and minus P1, sorry. And you would continue to change these as you're conducting your binary search on these arrays. Okay, that was a lot, so let's actually get into the problem here. Okay, first thing we should consider, we want to make sure, let's get the lengths going here. M equal to len nums1, right? Yes, and n is equal to len of nums2. And we want to make sure that this is the case. Remember over here how we said to start off, we want to make sure the smaller array is equal to m over 2 for the problem's sake. So let's do this. If len nums1 is greater than len nums2, then we're just going to return this problem, but with num1 and num2 switched. Oops. Okay. That looks good to me. All right. We also want to consider some cases where this wouldn't work before we jump right in. And what cases would those be? If both of them are equal to none. I'm sure they won't even give us that, but just in case. We'll just return none. And I'm going to import statistics to save myself some time on something that I'm about to do here. If, let's say, m is equal to 0, but m isn't, then we're going to just return the median of n, of nums1. Sorry, nums2, I should say. And that's because, well, m is always going to be less than n. So if m is going to be equal to 0, n won't. And the reason I'm doing this is because I don't really want to check to see if n is even or odd, and then, you know, based on that, find it. This is just saving me some time. It's going to be in constant time. It's just checking the middle element or the middle two elements. Anyway, what should be next? Maybe we should, okay, well, we are going to be conducting some kind of a binary search, right? So we want to make sure that our elements, our array has some area that we're searching, right? We'll call it the start and end. Say the start is equal to 0 and the end is equal to m for now. And then we're going to conduct this binary search until we find the median. So let's say while true, because we're always going to find the median at some point. We need to do a couple of things now. Now we get into the meat of the problem. first thing that we have to do is basically find out whether or not we have to find the actual partitions, the partition values. So we're gonna start like this. P1 is equal to start plus end over 2. And we're going to do another parenthesis here. Why is this? Because remember over here that we set P1 equal to M over 2. Similarly, for P2, how do we want to approach this? We just want to, well, we're going to be changing only P1, and P2 is dependent on P1. So I think that we should probably just be able to write what we wrote over here. Int M plus N plus 1 over 2 minus P1. I hope that should work. All right. Okay. So maybe we should check some things. If, okay, you know what we want to do? We want to make sure that we define some values. We want to define the elements that we're looking at. That'll make us a whole lot easier. We'll call these the left values. And we'll call these the right values, let's say. So P1 is equal to nums1 of P1 minus 1. It's going to be the element right before the halfway point. Why did I do P1? Sorry, let's call that left 1. Say left 2 is equal to nums2 P2 minus 1. Right 1 is equal to nums1 of P1. And right 2 is equal to nums2 of P2. Okay. Oh, something else I have to think about quickly before I get onto this is that we are going to reach a point in a lot of these where we're actually going to reach the very end of the array. And let's see if maybe that's the case over here, and that'll run us into some problems. Let's look at this one, 1, 3, and 2. Now we know from our partition here that we're creating the partition for this one, which is M over 2. 1 over 2 is 0.5, which is 0. So the partition is going to be right here, right? And that immediately causes a problem because there's no index for left 1. What we can do though is say at this point we can make an imaginary index equal to -infinity, let's say, and this should still work. And I'll show you in a second why. And so our second index would then be 3 plus 1 over 2, which is 2, minus 0, which is still 2. So our second partition would be over here. Let's also create a positive of infinity over here, so this would work. And obviously -infinity is less than positive infinity. 3, however, is greater than 2, so we need to change this partition. Let's put this over here, this one over here, and get an infinity over here. 1 is less than infinity, 2 is less than 3. And this is an odd number, so we can choose 2. And this will always work. So we need to make sure that when we are about to run into an error, we just create these extremely large values so that it doesn't. So let's say if P1 is equal to 0, then left 1 is equal to float negative inf. This is something you can do in Python, which is kind of cool. It gives you the lowest possible value. And else it's going to be equal to this. To save myself some time, I'm going to copy this and do this a bunch of times. Okay, and on the right side, we're going to say if P1 is equal to M was the size of the left one, then we're going to make this positive infinity. And otherwise, it's going to be equal to this. I'm going to call this one, sorry, right one, and right one. If this one's equal to N, right 2, right 2. Okay. Bear with me, guys. I know this is going to be a long one. This is not necessary. This is really not a very easy problem. All right, but we've come a lot of the way. Now we need to check if it's met the conditions to be the median, the values that we're looking at. So we'll say if the one on the left side on the first array, so if left 1 is less than or equal to the one on the right side, right 2 on the other array, and left 2 is less than or equal to right 1, then we've actually met our conditions, and we will be returning a number at this point. So we have to check first if it's even, and to do that we'll use the mod function. And remember, if it's even, then we want to be returning the maximum value on the left side and the minimum value on the right side and their average, because if you can imagine a line of numbers, the minimum value on the right side, the maximum value on the left side is going to be the largest value in the smallest group and the smallest value in the largest group. So return max left 1, comma left 2 plus min right 1, right 2, and you want to divide that by 2. And if this is odd, we're going to simply return the maximum of the two elements on the left side, because that will be the, because of the way that we've created this, where we do n plus 1, we are always going to have more values on the left side than on the right side. That's why we had it like that. Then we want to choose the larger of the two elements on the left side, because that'll be actually the middle element. It's not really supposed to be in the left group. So we return max of left 1, comma left 2. Okay. What other situations are there? Well, there's the situation where left 1 is greater than right 2. And what happens at this point? What happens if the left element in one of these arrays, let's say this element, is greater than this element? Or yeah, we probably should just look at the actual example where that's happening. This element over here, let's say this is array 1, this is array 2, is greater than this element here. We want to make sure, again, to set the partition on this side of that element at the midpoint. That's because we're doing a binary search and you want to check the new midpoints, right? So we then edit the start, and we want to edit the starts and ends respectively here, right? So how would we go about doing that? If this one's greater than here, then we want to edit the end, I think. Hang on, sorry, I gotta check the word just to make doubly sure. Okay. Yeah, we want to be editing this ending spot here. Make this equal to P1. Say that was the first array. Because now we're making the end the halfway point, right? And this would be our new start over here. Sorry, over here. This would be our new end. And we're going to do halfway between those to make this our new partition value. So end's going to be P1. And if that's not the case, let's say the only other possible case is that left 2 is greater than right 1. These can't both be the case. And if you don't believe me, you can do that with a simple proof by contradiction. Hey guys, want to apologize for that. My video stopped working for whatever reason at that point, so I'm just going to continue from here. This is where we left off, I think, around this point. I went a little further by accident and I didn't realize it wasn't recording, but I deleted my work and we're over here. Anyway, I believe what I was talking about was that the fact that the only case we could possibly have, other than the left element here being the greater than the right element there, is that left 2 is greater than right 1. And we can't have it be the case that both of the elements on the left side are greater than both of the elements on the right side. And I guess I could just draw up maybe y. Let's say we have L1, L2, R1, R2, where L1 is greater than R2, and L2 is greater than R1. If this was the case, then L2 would also have to be greater than L1, because L1 is less than R1, right? But since R2 is greater than L2, this assumption here is contradicted, so we can't have that be the case. So, sorry, don't know why I have that there. So otherwise, we should just have it, we should update the start and make that equal to P1. And that's because in this situation, for the smaller array, we would be moving towards the right, because our left element on the second array is greater than the first element on the right, the second element on the right array, the right element on array 1 is less than the left element on array 2, meaning that we want to move towards the right on array 1. So to do that, we would have to adjust the actual start point, and we'll make that equal to P1. Okay, with that in mind, let's try and run it. I also added some stuff, P1 and P2. This should be inf, not negative inf. I want to print these to kind of show you what's happening as we go along. Okay, looks like we might have a problem somewhere. Okay, you know what? That's a little tough to read. Let me do this real quick. Okay, interesting. So we're at a point where our start and end are not changing. Let me just create a different test case here to maybe get a better picture of why this isn't working. See if it works on this. I doubt it, but let's just give it a look. See, okay, it doesn't seem to be working. Okay, interesting. It's getting stuck at this point, where we're changing our start value across it, and eventually it gets stuck at 3. Doesn't increase. And why is that the case? Why is our start never changing here? It's always going to be P1. Okay. That's probably why, because our start here is eventually reaching the point where it goes in as P1. So if we reach this statement, start and P1 are not actually changing. And we want start to eventually be this edge point 4 in this situation. So if start is equal to P1, do start plus equals 1. And we'll do this in case it's not. Similarly over here, if end equals P1, we would do the complete opposite. Hopefully this should work. Nice. Okay. Great. Let's submit it then. Maybe before that, I want to exemplify something. It's gonna take a second. Sorry. And let's do. I want to get 32 elements to show you guys that this is running in fact log event time. So you should probably skip past me typing this because it's going to take a second. Okay, so we run it, and we're taking 1, 2, 3, 4, 5, 6 steps. And yes. And that would be appropriate for this. We're gonna have 32 elements. That's going to surpass the tree of 2 to the k minus 1 with 31. So it would be inside the next tree. This is the worst case scenario, but it's still approximately O of n, O of log n, I should say. If 31 and below, it's going to take max 5 steps. Remember, 2 to the k minus 1. But here, takes worst case 6 steps. But okay, O of log n. And we submit it. Let's just submit it now. And look at that. The runtime is fantastic. Better than 96.93% of other solutions. All right, thanks guys. This is a tough one, so thanks for those who stuck with me the whole time. Hope you guys learned a lot from this video. Certainly, I hope it was informative. And if you want to see more like this, just remember to like and subscribe. All right, have a good day, everyone.